Okay, so we're finishing up 12.7 at applications of exponential and logarithmic functions. Let's do a little bit more about the interest, and we will move on to 13.1 today. Yeah, so let's start. Okay, now 125, and we want what? What is it? 12.7? 12.7. Which one is 12.7? Applications of exponential functions. Is it this one? Is this where we finished? Okay, yes. So let's do more. Yeah. So, for example, okay, so let's talk about doubling time. So we talk about two formulas. So number 2. So number 2, okay. How long does it take? How long does it take to double the amount if the interest rate is 6% compounded continuously? So that is the question. Yeah. All right. Now, let's talk about what formula we're going to use. What formula are we going to use? Yes. So A is equal to P E raised to the RT. How come I use this formula and not the other one? Yes, we're talking about compounded continuously, not many times a year, right? So that's why we are using this formula. Now, what is given to double the amount? So what is given? So given, not answer, but let's write down the given. This is the formula. The amount is what? Double the original, so 2 times P, right? Because the original is P, the principal, it's 2 times P, even though I don't know the original. And what else do I know? 6%, what's that? R is equal to decimal, 0.06, yeah? So what do you want to find? Find the time, which is P, so let's answer this. A is equal to P E R T. So A, what do I put for A? What am I putting for A? 2P is equal to P E raised to the 0.06 T. So I need to find P. Okay, you guys know how to do this. This is an exponential equation. What do we do with exponential equation? Divide both sides by P. Yes. So 2 is equal to E to the 0.06 P. And then? What do we do next? ln both sides? Yes, that's right. So ln2 is equal to 0.06p times ln e. So what is ln e? 1. Yes. So how do I solve for t? Divide both sides by 0.06. So t is ln2 divided by 0.06. What is this approximately? So we need to use your calculator, right? 11.5? 11.6? Yes, because this is years, right? How long does it take? It's 11.6 years. So it takes approximately 11.6 years, yes, to double the amount. Wow, that takes a long time, right? Yes. All right. Good. Yay. All right. So now let's see. Let's do one more about the interest, because I think this is important. All right. We talk about chemistry. Okay. Suppose, no, that's not much. Let's talk about population growth. Yes. So the next one is population growth. So the next example, number 3. Okay. So in 2000, there were, this is 2000, is a long time ago, approximately 12 million text message. Oh, by the way, I have to write down the formula first. It is for 12 is this is just not a good book. So P of t, well, P of t is equal to P naught e to the kt. So this is almost the same as the interest rate. It's just it's using a different letter. Yeah. 12 million text messages sent each month. All right. This number has increased exponentially at an average rate of growth of 108% per year. Okay, now the question is, so A, find the exponential growth function. That models the data. Right? Okay. And B, estimate the number of text messages sent each month in 2009. All right. So let me talk about the formula a little bit. Does the formula look familiar? Almost. It's almost the same as what? A is equal to PERT. It's just using a different alphabets, right? Different alphabets, yes. Okay. Are you guys ready? Yeah, okay. So this one is P of t is equal to P naught e to the kt. So if you compare this, I could write any, using any letters, actually I could write y of t equals to y naught e to the kt. Or before, we used this already, a is equal to p e r t, right? So any letters that we use is fine. But P of t, this is the population or the amount or whatever it is, population or amount at time t. And P naught, what is P naught? The initial population or initial amount. What is K? This is the growth rate, rate of growth. Growth rate. And then what is T? T is the time or duration. Or time. Okay. So now let's look at the text message again. Do we know the initial population? So what is given? We know we will use P of t is equal to P naught e to the kt. What is given? 12 million. What is that? Initial. So P naught is 12, but million. So I'm just going to use my 12. Okay. What is, do I know K or T? Do I know K? K is do we know the growth rate? What is the growth rate? Yes, 108%. How do I change this to decimal? 1.08. Yes. Good. And what do you have to find? A is model. B, what do you have to find in B? P of t when t is 2009. When year 2009. Yeah. Okay. So when year is 2009, but not when t, but when year is 2009. All right. What is p then? P is 1. Because we're talking about 2008, and 2009 is 1 year after 2008. Yes? All right, so let's answer. Oh, this is 2000? Oh, so then this will be 9, right? Yes. Right. T is 9. Now, let's write down the formula. P of t is P naught e to the kt. So P of t is P naught. Do I know P naught? 12 e to the 1.08 t. Done. This is the model. How do you answer B? Yes. P of 9 is equal to P naught e to the 1.08 times 9. P naught is 12. So can we calculate, please? What is P of 9? All right. Oh, there's my calculator. Yes? 12 multiplied by, so be careful when you use your calculator, you have to put parentheses here. 1.08 times 9. So 12 e raised to the 1.08 multiplied by 9. So what's the answer? Mm-hmm. 199,766. Yes. Mm-hmm. So 199,766.9 million. So this is approximately what, 200,000 million? Is it? Oh my gosh. So it's a lot, right? So when it started in exponential grows really fast. When it started in year 2000, only 12 million per month. But what about in 2009? 200,000 million of text messages sent per month. What about right now? How many text messages do you send a day? None. Well, that's not common. Like, what about you guys? How many do you guys send? Only 2? But don't you do Line or WeChat? No? Oh, okay. Skype, do you Skype or Line or WeChat or WhatsApp or something like that? Or Facebook? Yeah, well, you don't use text message anymore. You use Facebook, right? Yeah, before there's no Facebook. Yeah, but 200,000 million. So exponential functions grow really fast. Okay. Now, is it easy? So basically what you need to do is fill this out, the P0, and usually the K is given. Right? Okay. So let's do exponential decay. It's the same formula. So this is exactly the same formula. If K is greater than 0, then we have an exponential growth. But if K is less than 0, then we have what is called exponential decay. All right. What decays exponentially? It is the amount of radioactive material. Yeah, like carbon. If you know that carbon 12, so let's do B. So is it B or C or D? I don't know. I don't remember anymore. Did I label it? C. So B is compounded interest. Okay. So now it's C. What did you say? What is A then? Hold on. Sorry. Oh, okay. Yes, got it. So this is exponential growth, yeah. And then so this is B2. So this is B2, exponential growth. And then B3 is exponential decay. B3 is exponential decay. Okay. So the formula is still the same. So P of P is P0 e to the KT. But what happens here? K is less than 0. So this is decay rate. When K is greater than 0, then it's a growth rate, average growth rate. This is average decay rate. All right. Okay. So let's talk about carbon dating. Have you heard about carbon dating? What is carbon dating? Right, by the amount of carbon. Yes. So we're not dating carbon, are we? No, you're not. Yes. So you don't take carbon on a date, but basically this is the process of the determining the age of a fossil or anything else based on the amount of carbon. Yes, you're right. The amount of carbon, yes, contained by the fossil. All right. So carbon has a few forms. There is a stable form, is carbon-12. So carbon-12, this is stable. All right. So it doesn't change. The amount doesn't change over time. But what is radioactive is called carbon-14. Is radioactive, meaning what? The amount change, decays exponentially. So carbon-14 is radioactive and it decays exponentially. How about carbon-12? Well, no, it's stable. Like gold. Gold is stable, right? It doesn't react easily. That's why if you have gold-plated things, even if you put into water or sweat or whatever, it doesn't change color because gold is stable. Now, well, carbon-12 is stable, it doesn't change, but carbon-14 is radioactive, it decays exponentially. Yeah. Did you remember I talked about the doubling time? How long does it take to double? Remember before? Now, this is half-life. So, what is half-life? So, half-life is the amount of time, the duration, the time. What is it, Johnny? It takes for a radioactive substance to decay to half of its original amount. All right. So it's called half-life. It's not doubling time. So this is half-life is versus doubling time. So, well, if it decays, it's not going to double. It's going to be less, right? All right. So half-life is the time for a radioactive substance to decay to half of its original amount. All right. Does that make sense? Because when you decay, it's not gonna be double. It's going to be half of it. Yeah. All right. Now, so should we start? Do an example. Okay. Let's see. Yeah. So, for example, I'd rather do it on the next page. So I'm going to write down. So this is used a lot in carbon dating. So to determine the age of fossil. All right. I think Dr. West has the what is it? The machine to measure how much carbon-14 is on in the fossils. So, for example. The radioactive element, carbon-14, has a half-life of 5,750 years. So what does it mean? If I say the radioactive has a half-life of 5,750 years. What does it mean? So after 5,750 years, what happens? It's half of the original mass. So this just means, so this is my own note, this means after 5,750 years, what happened? The amount of C14. So this is how we write it. C14 is half its original amount. Original amount. Does that make sense? So the mean is not part of the problem. So you have to be able to interpret it that way. All right. Now, recently, while digging in, what is it? Chaco Canyon, New Mexico. So this is from the book. So I'm just going to follow. Chaco Canyon is in New Mexico. Archaeologists found corn pollen that have lost 38.1% of its carbon-14. So C14 is carbon-14. Yeah. So it's talking about the Indians have been cultivating crops in the southwest centuries earlier than scientists had thought. What was the age of the pollen? So archaeologists want to know how old they are. All right. Okay, so what do you think will happen here? So first we have to find K, right? Because we don't have K. Do we have K or not? No, we have to find the model. So what is given? Half-life is 5,750 years. So what is given? P of T is equal to P naught e to the kT. This is what we're going to use, right? Now, let's talk about the half-life here. So what are we supposed to do here? What are we supposed to do here? How do we translate it here? P of 5,750 is half the original amount. So that's what I wrote. So after 5,750 years, the amount is half the original amount. Is it? Okay. Good. And then find T. Find T when P of T is equal to 1 minus 38.1% of T naught. This is a little bit difficult, so you have to look at it a little bit more. Yeah. So first we have to find K. How do we find K? Well, P of T is equal to half P naught. P naught e to the kT. Do I know the P of T? Do I know the P of T? Well, yeah, it is half of P naught is equal to P naught e to the k times. Do I know the P? 5,750. All right. Yeah, this is one of the most difficult. And then how would I solve for k? Because I need to solve for k. So this is line k. Divide by p naught, right? Divide both sides by p naught. Yes. Oh, because it says it has lost, right? Yeah, so this is 61.9%. Because it says it has lost 38%. So so what is left is 61.9%. Because it says it has lost 38.1%. All right, good. Now, anyway, how do I solve for k? So half is 0.5. Let me just write 0.5 is e to the 5750k. All right, then what do I do? ln both sides? Yes. So ln 0.5 is equal to 5750k times ln e. All right. Good, then what? ln e is 1, yes. So divide both sides by 5750. All right. So what is this equal to? K is ln 0.5 divided by 5750. Do you want an approximate value? So, but here you cannot just cut it. You have to get the whole decimal as much as possible. So ln 0.5 divided by 5750, that is negative 0.000120. Did you guys get the same thing? 120547. Yeah, you can, as long as you know how to calculate it. Yeah. So P of P is equal to P naught e to the negative 0.000120,547 P. Why do I carry this many decimals? Because this is in the middle. I do not want to round in the middle. Yeah, because the answers might be a lot different. Are we okay so far? So that's your model. So once we have the model, then we're done. We could answer the question. So we always start with model, and then we could answer the question. Yeah. All right. So how do we answer the questions here? So we're done with K. We're done with the model. How do we answer the question? So 0.619 P naught is equal to P naught e to the whatever it is, right? So once you find the model, you're answering the question. Then how would you solve this? Divide both sides by P naught. Oh, I'm sorry. I'm waiting for questions. Are we okay so far or no? No? Where are you guys confused? Let me backtrack a little bit. The whole thing? So let me backtrack a little bit. I'm waiting for questions. So do you understand what they're trying to do? What are we trying to do? Determine the age of what? Fossil. So they found a corn pollen. Do you know what a corn pollen is? Like a corn seed, right? Why is it important for archaeologists? Any idea? Yeah, why are they digging in New Mexico? And then they found a corn pollen and they want to know the age. Why? Yeah, see who lived there and who did plant something a long time ago and how long ago what it was, right? So they suspected some Indians to be there and then planted something, and they wanted to know how old were they, right? Okay. Now, how are they going to determine that? They're using the amount of what? Carbon-14, right? Okay. Why is it carbon-14 and not carbon-12? Carbon-12 is stable, so it's going to stay with the corn. What about carbon-14? It's radioactive. What does it mean if it is radioactive? It decays exponentially. So we know it will follow this model. If it decays exponentially, anything that decays exponentially will follow this model, right? Okay, so now what is given is half-life. Carbon-14, any carbon-14 in mummies. That's how they determine the age of mummies, by the way. Age of any fossil is by carbon dating, yeah? So we know that the half-life is 5,750 years. So what does it mean? So after 5,750 years, then what? It's only half of the original amount. That's why I wrote this. The half-life is 5,750. It's this one right here. So after 5,750 years, the amount is half the original amount. Okay, I'm waiting for questions so far. No questions so far? Yes, Melissa. Oh, okay, yes, that's next. Yeah, I'm answering that next. But up to here, the half-life, is it clear what half-life means? What does half-life mean? The time it takes to what? To half the original amount. So of course, this is decay, it's not double. What is doubling time? If I ask you, what is doubling time? The time it takes to double. But half-life is the time it takes to become half of the original amount. Does that make sense? So you can, like, it's versus doubling time. Yeah? All right. So that's why I have this. Now, the archaeologists found corn pollen that had lost 38.1% of its carbon-14. So if it lost 38.1% of its original carbon-14, how much is left? Yes. So it lost 38.1%. What about what is left? So this is what you should think about. What is left on the corn pollen? How many percent? 61.9%. Does that make sense now? Okay. Because it lost 38.1%. So what is left is 61.9. That's where the 61.9% comes from. Make sense? Okay, now the way we do it, we write down the formula, which is the exponential decay formula, right? And we know that P, this is 5,750, and we know the amount is half the original amount. So after 5,750 years, the amount is half the original amount. So that's how we wrote that down. So far so good? Okay. And then we solve for K. So we got K, we got this K, and then we put it here. That's your model. Done. So first thing is always finding K. It's not given. I'm not given what is the decay rate. Okay. Now, Do I know the age yet? Do I know the age of the fossil yet? No. So what are you going to do now? You already know the model. Yes. So I'm going to use this information. So what's left? 0.619 of the original amount is equal to the amount, the original amount, 0.000120547 P. So basically, I want to find the H. The H is this P right here. That's what I want to find. Yay or nay? Yay? Double? So this is what's left. What's left is 61.9% of the original. Okay, now what am I supposed to do? How am I going to solve it? Divide both sides by P naught. You're right. Okay, good. Then what? I need space here. ln both sides? Okay, so when we have ln, then we have ln 0.619 is equal to negative 0.000120547 P times ln E. All right, and ln E is 1. Okay, good. Now what? Yes, divide both sides by negative 0.000120547. Okay, I'm sorry. You do have to carry this much because otherwise your answer will be different. Because this is exponential and in the middle. Okay, so what is approximate value of P? Ooh, wow, they did the farming that long? Yes. Yes, so ln 0.619 divided by negative 0.000120547. Oh, 3,900, approximately 4,000 years ago? Wow. So the age of the corn pollen is approximately 4,000 years. Wow. That's amazing, isn't it? So, they started agriculture 4,000 years ago. So that's how the archaeologists say about how old is the mummy. They approximate how old is the mummy. They use this. They really use this. So next time you see an archaeologist, you know what to do, right? You know how to calculate. Yes, no? Okay. All right. So now, anyway, I'm done with 12.7. So we have a test on Wednesday, right? Yeah. Okay. So I don't think I will ask about decay. So if you think this is difficult, it's okay. I probably wouldn't ask this question. I know it's difficult, but anyway, you have to see it, because when we get to Math 245 or Math 260, you'll see this again and you say, I know this. Yeah, okay, you know already. Yeah. So are you guys going to download the sample test? Okay, and so tomorrow we'll discuss it and start chapter 13, okay? Circles. All right. Okay, guys, thank you for coming. And I'm sorry about the trouble with the projector in the beginning. Yes? So see you tomorrow. Remember sample test. Yes? So if I were you, I'm going to study the interest. The interest? Yeah. All right. Okay, guys. I will see you tomorrow. Yeah? All right. Okay, so we're finally done with applications of exponential and log functions. Tomorrow, Yes, you too. Thank you. Tomorrow we'll start chapter 13 and discuss sample test chapter 12. Okay? And we have a test on Wednesday.